Mr. here back in the wood shop. We're talking Module 6, Lesson 3, Names and Formulas of Ionic Compounds. So today we're going to learn how to write formulas of ionic compounds as well as how to name ionic compounds. And this stuff is really important because this is what we use to communicate in the chemistry world. So, of course, our focus question is, what are the names and formulas for ionic compounds? And probably more importantly, how do we derive them? Okay, here's some vocabulary words that you can write down and keep track of as we move through the lesson. And as a review, we do need to know the difference between a nonmetal and a metal. So remember, on our periodic table up here in this corner, we have the nonmetals over here, and then pretty much we have that stair-step line here. Everything to the left of the periodic table, or on the periodic table, is considered a metal. Okay, so it's important that we know the difference between a metal and a nonmetal, and that ionic bonds occur between metals and nonmetals. Okay, so in ionic compounds, we have what's called a formula unit. Okay, and you'll see a formula for a ionic compound such as NaCl, so sodium chloride. But that NaCl it's in a 1-to-1 ratio, so 1 sodium for every chlorine. But in an actual sample of sodium chloride, we will have a whole bunch of them. We have a huge clump of sodiums and chlorines all together, and so the formula that we write for sodium chloride is just the simplest ratio of those ions together, and that's called a formula unit. So in the case of sodium chloride, like I said, it's a 1-to-1, so we'd have Na and then Cl. But in the case of magnesium chloride, you would have twice as many chlorines as you do with magnesiums, because magnesium's a 2+ charge and chlorine's a -1 charge. We have to balance those charges out, and we would need 2 times the number of chlorines we need twice as many chlorines as we have magnesiums. Okay, so that's a 1-to-2 ratio, so we would write magnesium 1 and then chlorine 2. Okay, so we're going to dive into that a little bit more and work on writing formulas for ionic compounds. Okay, so to start off with, we have monatomic ions. Monatomic ions, so mono is 1, so monatomic, 1 atom. So monatomic ions are just things like magnesium or bromine, in this case the bromide ion. So it just has 1 atom in that ion. Okay, and what's going to be important and helpful in identifying whether you have 1 element in that ion or you have 2 elements or 2 or more elements in that ion are capital letters. Okay, keep track of capital letters. Notice we only have 1 capital letter here, so that's 1 type of element, so that's monatomic. Okay, so here's a whole list of some common monatomic ions and their charges. We've covered this in a previous lesson. So here's the rules for writing formulas. Let's just get right into it here. So the symbol of the cation always goes first. And the cation is the ion that forms a positive charge. So that's going to be your metal. Okay, we're always going to see the metal written first. Remember the first rule in chemistry? There's always an exception, except for the first rule. Okay, so there are exceptions, but for the most part, 99.9% of the time, you're going to be writing the cation first and then the anion second. Okay, the subscripts represent the number of that ion in the formula unit. And if a subscript is 1, we just don't write it. Because if we've written the symbol, then obviously there at least has to be 1. Okay, if that was not the case, then we'd have to write the symbol for everybody every single time. And that would just be insane. So we write just the symbol, leave it. We don't write a 1. But if it's any other number, 2, 3, 4, we write those. This is really important, that the total charge of the compound has to be equal to 0. Okay, and so that's why we end up with the different ratios, is it's based off of their charges. Okay, so let's go ahead and work through an example here. We need to determine the formula for the ionic compound formed between potassium and oxygen. So maybe take a moment to pause and look those up on a periodic table and see, maybe try to see what charge they are. Try to remember what charge they make when they form ion. Okay, were you able to figure out their charges? Let's take a look. So potassium forms a +1 charge because it's in that first column, and oxygen's a 2- charge. Okay, so you can already see that what's the ratio we're going to need in order for those to add up to 0. So plus 1 times what? Plus the 2 minus charge times however many we need there has to add up to 0. Okay, so I think hopefully you can see that you're going to need 2 potassiums for every oxygen in order for them to add up to 0. So our formula is written here in red, which is K2O. Okay, so we can see the formula here. We have, if we have 2 potassium ions and it's a plus 1 charge per ion, okay, then we would end up with a 2+ charge for this area right here. And then we're going to add that to 1 oxygen ion that has a 2- charge, so that's a -2. So here we go, we got 2 of the plus 1 charges plus 1 of the 2- charges, and that all is going to add up to 0. Okay, so here's a you try. Go ahead and pause the video and see if you can solve this one on your own. All right, how'd you do? So the trick is that you got to look these up on a periodic table, figure out what their charges are, right? So what's the charge of an aluminum ion? Well, that should be a +3, and a sulfide ion is going to be a 2- charge. Okay, so aluminum +3, sulfide ions a 2- charge. So what is their ratio going to be? Well, I'm going to tell you a little, well, let's look at the answer here. We're going to need 2 aluminums for 3 sulfurs. Okay, and there's a little trick here. Notice how the charge, with the charges, there's a little 2 up there. That's going to come down to the bottom and become a subscript 2 for the aluminum. The 3 charge on the aluminum is going to come down and be the subscript of sulfur. So they kind of do this little crisscross thing. And that's kind of a little trick that we can use. Oftentimes it works out. Sometimes it can get us in trouble, but maybe we can talk about that in class. Okay, so there we see the math here. We have 2 of the 3+ charges. We have 3 of the 2- charges. So they all add up to 0. We are good to go. Now, what happens if we don't have a monatomic ion and we have polyatomic ions? Polyatomic meaning many atoms. So how are we going to identify these? Remember I said the capital letter thing? Well, look at this. We have 2 capital letters. That means we have 2 different types of elements in that ion. So these are polyatomic ions. And the nice thing about these is once you identify them, you just write their name. You don't have to change the names. You don't have to do anything else. You just have to write their names. Okay, so that would be with naming. But with formulas, we just balance them as if they're one big blob. So this whole blob of NH4, we keep it as NH4, but that whole group has a +1 charge. And then at that point, we just treat it just like we did with the monatomic ions. And if we need to add up to 2+, then we just multiply it by 2. And I'll show you how to do that. Okay, so here's a list of common polyatomic ions that we may run into, and I've actually included these on your Pretty Purple packet on the bottom of the second page of your reference sheet. Okay, and so we will try to stick to these polyatomic ions in class. Okay, while we're here, I do want to point out that up here there is a whole list of positive cations and their charges as well. Okay, so here's the rules for writing formulas of polyatomic ion compounds. So since the polyatomic ion exists as a unit, never change the subscript. So if you have NH4, let's go back here. We got NH4 right here, ammonium. You're never going to change that 4. Because if you change that 4, you no longer have ammonium. Okay, like right here, this is nitrite. If we change that 2 to a 3, then we have nitrate. Now we have a whole different chemical. Okay, so don't change those subscripts. Okay, if more than one polyatomic ion is needed, then you need to use parentheses around that group of atoms and put a subscript outside the parentheses. So let me show you a couple examples here. So here's sodium nitrate. Sodium is a +1 charge, and nitrate, the NO3, is a -1 charge. So they're already balanced. So this would be the correct formula for that. But what happens if we have barium nitrate? Well, barium is a 2+ charge. Nitrate's a -1 charge. So we would need 2 of the nitrates to balance out the 2+ charge of the barium. And how we write that is we put the nitrate in parentheses and then we put a 2 outside, saying that I need 2 of this entire polyatomic ion. Okay, notice that the 3 stays the same so we can identify it as nitrate. All right. So let's go ahead and do an example here. We got a compound that's formed between calcium ions and phosphate ions. And that ATE right there, phosphate, is going to be a clear indication that you're dealing with a polyatomic ion. Okay, the 8s and the ites are, so ATE, ITE, those are good indications that you're dealing with a polyatomic ion. And with practice, you're going to get used to identifying what these are. Okay, so we have calcium and phosphate. Calcium's a 2+ charge, phosphate's a 3- charge. So what is the ratio between those to add up to 0? Well, if you use the crisscross method, you would see that this 2 would come down here. We would need 2 phosphates and we would need 3 calciums. And in fact, that is exactly correct. We would need 3 calciums for every 2 phosphates. Notice the parentheses and 2 of the entire group of phosphate. Okay, so the next one, let's talk about oxyanions. Okay, many of our polyatomic ions are oxyanions, and that means that they are anions, so negative ions with some element bonded with oxygen. Okay, so if we look at nitrogen here, we have nitrogen that has O3. We have nitrogen that's bonded to 2 oxygens. So here it's bonded to 3 oxygens. Here it's bonded to 2 oxygens. Same thing with sulfur, except there's 4 oxygens and 3 oxygens. These are called oxyanions, and there is a certain naming convention with those. We're not going to get into it, and so you can kind of see it here. We're not really going to get into that. We do this a little bit more in AP. But I've written out, or we've given you the reference on your reference packet. We're going to stick to these. It's going to be as simple as just looking these things up and writing their names. Okay, and you can see that many of the polyatomic ions are in fact oxyanions. And you can see, like, here's your nitrate, NO3, and your nitrite, NO2. So at this point, what I really want you guys to know about these is that be careful with looking and pay attention to the details of how many oxygens are on that polyatomic ion, because it matters, right? If you look over here at carbonate, that's CO3, carbonite is CO2. If we look down here, sulfate is SO4, but sulfite is SO3. Okay, so please pay attention to the number of oxygens. All right, so naming. What happens if we gotta go the other way? So naming them. Well, we name the cation, or sorry, the cation before the anion. Okay. So again, just like the formula, the cations first, the anions second. So positive, then negative. All right. So for monatomic cations, use the element name. So just like sodium, barium, potassium, iron. Right. You just use their name. Okay. For the monatomic anions, here's the change. For a monatomic anion, so that would be the negatives, like the fluoride, the chloride, the bromide. Notice I'm not saying fluorine, chlorine, bromine. I'm saying fluoride, chloride. Okay, we're changing that ending to IDE to indicate that it's in the bond. Okay, it's in that compound. To distinguish between multiple oxidation numbers, so some, okay, what does this mean? Transition metals, those metals that are in the pit, they can have multiple charges. They can have +2 charges, +3 charges, +1 charges, okay, to indicate which one we have, which charge is on that ion. So, for example, iron could be iron 2+, or iron could be iron 3+. So which one is in the compound? Well, in order to indicate that, we write a Roman numeral number behind its name. So it would say iron, and then Roman numeral 2, and then whatever the anion is. Okay. And then when the compound contains a polyatomic ion, really simple, just use the name of the polyatomic ion, and that's it. Okay. Here's a chart that we'll give you in class that you'll have as reference, and you have basically just a flow chart of questions. So is there a metal in the compound? Yes or no? And if it's yes, then you go over here. Is the metal a transition metal? No or yes. And then you keep going through there, and it goes through the sets of rules. Okay, so if it's not a transition metal, we're going to go over here, and we're going to say, well, you just name the metal and then name the non-metal. Or if there's a polyatomic ion in there, then you name the metal, then you name the polyatomic ion. Okay. Over here, not a polyatomic ion. We're going to name the metal and then name the anion, but we're going to change the ending to IDE. Okay, so become really familiar and use this when we're practicing writing names. All right, so I think it's time that we practice a few of these things, right? So here I give you the elements that are going to form, or actually the names of the ions that are going to form a compound. I want you guys to write the formula. So go ahead and pause the video and see if you can write those formulas. All right, let's check to see how we did on those. So we got aluminum oxide, we got beryllium nitride, and magnesium sulfide. Okay, and take a look at the answers. So aluminum is a +3 charge, oxygen or oxide is a 2- charge. So we would have the ratio here. Remember, we can do the crisscross method. Okay, and here's where it gets you in trouble. The crisscross method gets you in trouble because magnesium is a 2+ charge, and so let's see. Magnesium is a 2+ charge, and sulfide is a 2- charge. If we crisscrossed those, then we would need a 2 and a 2 down here, right? But we don't write the 2's and the 2's because a 2-to-2 ratio is the same as a 1-to-1 ratio, so we reduce it to its smallest whole number ratio. So watch out with the crisscross method. That's what's going to get you in trouble. Okay, watch out for those 1-to-1 ratios. All right, go back to here. Okay, go ahead and try these ones. Pause this and see if you can get these ones. All right, here we go. I realized I didn't give you much time on that to pause it, so pause if you need to. But here's the solutions. Ready? We got sodium nitrate. Ooh, 8. Look at that. We got 8, 8, 8. What did I say about the 8s? Polyatomic ions. All right, so we look them up in the chart, and we balance all their charges. So we're going to need some parentheses in there. You can check your answers with the solutions there. Okay, next, let's do, hey, let's go the other way. So write the names of these formulas. So I give you the formula, you go ahead and try to write the names. Ready? Pause in 3, 2, 1, pause. All right, how do we do on these? Maybe it's a little bit more helpful if we take a look at our flow chart. Remember up here it says, is there a metal? Well, of course there's a metal. We're dealing with ionic compounds. Okay, so is there a metal? Is it a transition metal? Let's take a look at this first one and work through this here. So we have NaBr. Na, so sodium is in the first column. That's not a transition metal. So no transition metal. Count the different elements. What did Mr. Ellert say about different elements? Oh, yeah. So count the capital letters is really what he means. All right, so there's 1 capital letter, 2 capital letters. That means you have 2 ions in this compound. Okay, you have a sodium ion and you have a bromine ion, right? So you have 2 elements in here. So we have a metal, we have a metal with a nonmetal, okay? So we're going to name the metal first, so that would be sodium, and then name the nonmetal second, but change its ending. So this is bromine, but we're going to change the ending to IDE, so we're going to end up with sodium bromide, okay? So the next one we have, do we have a metal? Yes, of course. Calcium. Calcium's in the second column, not a transition metal. So we're back over here again. How many elements? Well, we have 2 capital letters. And you're like, but Mr. Ellert, there's a 2 here, so that's 3. No. 2 different elements, okay? There's a calcium element and there's a chlorine element. That's only 2 different elements, right? So we're still hanging out over here. We're going to name the first one, that's calcium, and the second one we're going to change the ending so we get calcium chloride. Okay, I'm going to jump down, so the next one here, you should have gotten potassium hydroxide. Let's jump down to this one here. Ooh, scary. Okay, so let's go through this. Do we have a metal? Yes, of course. Okay, who is our metal? Our metal is copper. Okay, it's a transition metal. Is it? Copper's in the pit. It's a transition metal. So, is it a transition metal? Yes. Yay, we get to go to the other side. Okay, count the different elements. How many different elements do we have? I have 1 capital letter, 2 capital letters, 3 capital letters? That's 3 or more elements. So now we're over here. Not only do we have a transition metal, but we have a polyatomic ion. Okay, so we're going to name this. How are we going to name this? Name the transition metal first. Copper. Okay, determine the charge of the transition metal. How do we know what the charge is? Well, here's the thing. Nitrate, if we look on our chart, nitrate, NO3, is a -1 charge. So if you have a -1 charge, but you have 2 of them, so that's a 2- charge, right? So total, that's 2-. How many coppers do I have? I only have 1, and it has to counterbalance the 2-, so that must mean that it's copper 2. So it has a 2+ charge. So this is going to be copper 2, and then we looked this up already on the chart, and that's nitrate. So this is copper 2 nitrate, and here's where the Roman numeral numbers come in. So this reads copper 2 nitrate, okay, with the Roman numeral numbers. It's a polyatomic ion. Nitrate is a polyatomic ion, so do not change that ending. Okay, the only time you change the ending is if it's a monatomic anion. Okay, and our last one here, maybe you want to pause again and see if you can try this one on your own. But here comes the solution in 3, 2, 1. Boom! We have silver chromate. You're like, but Mr. Triller, you have a transition metal, and you don't have a Roman numeral number in there. Well, what's the first rule in chemistry? There's always an exception. Okay, and silver is always a +1. So everybody in the chemistry world knows that silver is a +1, so we don't write the Roman numeral number. Okay, there's actually 3 elements like that, and maybe we'll discover them throughout our journey. All right, let's go ahead and check our understanding and get on out of here and go practice some homework or something. So check for understanding. Here we go. Question number 1. As always, pause, then advance for the solution. Here comes the solution. Okay, number 2. And our solution. Number 3. And our solution. Number 4. And our solution. Number 5, bonus number 5. And the solution. Okie dokie. Hey, this one's the rare. Is there a metal? No, there's no metal, but guess what? It started with a polyatomic ion, and this polyatomic ion here, NH4, is ammonium, and that's the one you really got to watch out for because it's going to sneak up on you. It's pretty much the only cation polyatomic ion that we deal with. Okay, so that's kind of a tricky one. All right, hey, that ends our lesson. It was kind of lengthy, but also kind of fast and quick. This stuff comes with practice. Practice. You'll get it. It'll click. We'll have fun. Let's rock and roll. Have a lovely day.